Okay, moving on with part 2, properties of liquids. So to talk about liquids, really the main things we need to talk about are vapor pressure and just pressure overall, equilibrium vapor pressure. So if we look at our two containers that are here, we're showing two different kinds of vaporization. So going from liquid to gas. So evaporation is here, and then here you're looking at evaporation, but it's at equilibrium with the liquid surface. So this vapor pressure has reached equilibrium. Let's talk about what that means. So vapor pressure or equilibrium vapor pressure has these symbols, and it's the pressure of the vapor above a liquid when the liquid and gas states are at equilibrium. So pressure really, just as a review, is just the force of these molecules hitting the sides of the container. That's all pressure is. If you have more molecules or they're moving faster, i.e. they're at a higher temperature or more kinetic energy, your pressure is of course going to increase. So if we were to look at an equation to show that, if we put heat in plus a liquid, A is just some substance A, and we're in equilibrium with substance A in the gas phase. And of course here's your Kp. So substances with a high vapor pressure, meaning they vaporize easily, are said to be volatile. And they're volatile because the forces that are holding them together, the IMFs that are holding them all together, are weaker. If they're weaker, those bonds can break easier, those intermolecular forces can break easier, allowing them to no longer be constrained in the liquid phase, and now they can break free in the gas phase. So anything that's volatile tends to have weaker IMFs. Okay, first question. How does the vapor pressure change at high temperatures? So take a second, please pause the video, and I'd like you to try to answer these 3 questions on your own, then come back and we'll review. Okay, so hopefully you were able to take a second and write down what you think. So how does the vapor pressure change at higher temperatures? Turns out as the temperature increases, you are putting more kinetic energy into your liquid. If you're putting in more kinetic energy, the molecules move faster. If they move faster, they can escape the liquid phase and go into the gas phase. If you have more gas molecules, you have more pressure. And that pressure above here is called vapor pressure. So your vapor pressure is going to increase. So, summarizing, as temperature increases, more molecules can escape the liquid phase. And so then overall you are increasing your vapor pressure, your PVAP. Alright, second bullet point. How does the vapor pressure change with a substance with a weaker IMF? We kind of already covered that. So if you have weaker intermolecular forces, it takes less energy, it's easier to happen, it's more likely that the ambient temperatures or whatever temperature that you are at is providing enough energy for that to happen. So it's easier for substances with weaker intermolecular forces to vaporize. So again, they have a higher vapor pressure. Alright, what is expected to happen if the pressure, so this is just the external pressure just pushing down here, is greater than the vapor pressure? What's expected to happen if the pressure is less than the vapor pressure? So if we talk about just this first part, so if our pressure is greater than the vapor pressure, if you think about this as your vapor pressure, if you had a lot of pressure pushing down on these molecules, you can imagine pushing them closer together. You're pushing them closer together, you're condensing them, and you're getting condensation. You're forming liquids. You're going from gas to liquid. And that's essentially what happens when it rains. When you have high pressure outside, all these high pressure systems push in on all of the water molecules. They coalesce them. They condense into liquid, which falls as rain. So if our pressure is greater than our vapor pressure of our same substance A, you're going to get condensation. So You're going to form a liquid. And the opposite is true. So here, if you had your pressure less than your vapor pressure, you didn't have a lot of pressure here, you're going to get a lot of these molecules being able to get out, escape the liquid phase into the gas phase. So you're going to get evaporation. So you're forming a gas. Alright, so that's all talking about vaporization. Turns out, and I kind of alluded to this at the beginning, there are two types. This is our general term, vaporization, going from liquid to gas. The first type is evaporation. That's the vaporization that takes place below the boiling point. That's just so if you leave, a puddle of water outside, you get some evaporation. It's not necessarily boiling, just the water molecules on the top. Some of them are able to escape that liquid phase. And then when molecules on the liquid surface escape to become gas, this happens when the atmospheric pressure is less than the vapor pressure. So again, for the same reasons as above, you can't have too much pressure condensing your gas molecules, or they're just not going to be able to escape. They're going to be pushed closer together. Those intermolecular forces are just going to be more attracted to one another, and you're going to get a liquid. Boiling is a vaporization that takes place at the boiling point, when vapor is forming below the surface of the liquid. And we've all seen this happen. Maybe if you have ever opened, those sodas in the clear containers they sell in the vending machines. If you've ever opened one of those, and before you open it, it looks just like watery and you don't see a bunch of bubbles inside. Then you open it, and the pressure changes, and now the pressure is at equilibrium, and you really are boiling it essentially for a second because all these bubbles are forming below the surface of the water. And you can see those moving to the top, and that's your carbon dioxide coming out. So this happens when the atmospheric pressure is equal to the vapor pressure. And the boiling point is the temperature at which the vapor pressure is equal to the atmospheric pressure. That's important. So go ahead and highlight or circle or underline that. The boiling point is the temperature at which, so it's a temperature, the vapor pressure is equal to the atmospheric pressure. That's this situation here, so I'm saying these are equal. Arrows up are equal to arrows down. So, looking at example 2, we can look at all of these on a curve. So we are going to consider 3 liquids, diethyl ether, ethanol, and water. What's the boiling point of each liquid when the atmospheric pressure is 400 millimeters of mercury? And remember, if you haven't memorized these, 1 millimeter of mercury, Hg stands for mercury, is equal to 1 torr. And we're going to be looking at this in torr, so you can imagine that just as torr. So for this problem, we're going to start at 400 millimeters mercury, or torr. I'm just going to draw a line across so I can keep track of what I'm looking at. So what's the boiling point of each liquid? Well, boiling point's a temperature, so if I follow the pressure over, hey, here's my boiling point of diethyl ether. Oh, that's about, 16-ish degrees Celsius. So diethyl ether is, about, and it doesn't need to be totally exact, 16 degrees Celsius. Let's keep going. Okay, next one is ethanol. Ethanol's right here. That's probably about 62, 63-ish, I'll say. So ethanol is, I'm going to say 63 degrees Celsius. And then keep moving along. And water, that boiling point of water at 400 torr is only 85 degrees Celsius, much lower than the 100 that we would normally see here at 1 atmosphere. So anyway, that's 85 degrees Celsius. Which liquids will be boiling at 50 degrees Celsius and 500 torr? So right now, if you can pause the video, I'd like you to try to do parts B, C, and D on your own, and then come back and we will review. Okay, so hopefully you're able to try that. Let's see if you got it right. So we're going to find our 50 degrees Celsius right here, temperature line. Here's 50 Celsius and 500 torr. Well, where do they intersect? Oh, right there. So this is for part B. So what is the only liquid that is boiling at this point? Well, we've only hit the boiling point of diethyl ether. We haven't hit ethanol, and we haven't hit water. So those boiling curves are here. So the only one that's boiling at that temperature and pressure is the diethyl ether. Okay, part C. Samples of the liquids at 20 Celsius are placed in a container at 800 torr, and the pressure is reduced using a vacuum pump. This is a fun one. So, you can actually do this and see this happen. It's pretty crazy. So, let's see, I lost my point. Okay, so 800 torr. So let's find our 800 torr. That's right up here, and we're going to do 20 degrees Celsius. All right, so initially we're starting here. Use a different color so I can show you what happens. So now it's saying that we're using a vacuum pump, so we're going to go ahead and decrease the pressure. So what order are these liquids going to boil in as we move down? So all you have to do is hold the temperature constant, it's 20 degrees again, and see what we run into first. So bam, diethyl ether right there. That one's going to boil first. And then we keep going, lowering that pressure until we hit ethanol and then finally water. So we're going to go down in that order, and diethyl ether, then ethanol, then water will begin boiling at 20 degrees Celsius just by reducing the pressure. So you can make something boil not only by increasing the temperature, but by decreasing the pressure, which is actually amazing to see. So first diethyl ether. First, then ethanol. Then good old water. All right, part D. Compare the strength of the intermolecular forces among the liquids using vapor pressures. So, as we know, when something has a high vapor pressure, there's a lot of vapor above it. That means the intermolecular forces were weak. So we're looking at the one with the weakest vapor pressure first. So that's going to be the one with the highest, or sorry, I mixed that up. The highest vapor pressure first, meaning that it's going to have the weakest IMFs. So let's rank the vapor pressures first. So PVAP of diethyl ether was highest, and that's going to be greater than the ethanol. Followed by the water. So from this, the IMFs are going to follow the same curve. So your H2O is going to have the strongest IMFs. So strongest IMFs. And your diethyl ether will have the weakest intermolecular forces. Okay, last thing. So we're looking at 3 different liquids here. Well, one of them is the same. So we're going to compare benzene, acetone, and water. And we're going to rank in increasing surface tension, then boiling point temp, delta H VAP, and equilibrium vapor pressure. The first thing you should do for this is to draw the Lewis structures. So just down here, just in this small little space, I'm going to draw the Lewis structures for you. So we'll do water at the very bottom, H2O. And we know water is insanely polar. It does hydrogen bonding, strongest IMFs that we're going to have. Your acetone looks like this. And this area here is going to be pretty polar. So you're going to have a lot of negative charge around this oxygen. But it's not so polar. It's not bonded to a nitrogen, oxygen, fluorine. So you don't get hydrogen bonding. This is just dipole-dipole. And then benzene, remember, is the one that had all those resonance structures before. This is totally symmetrical. So for benzene here, we don't have, the only IMF we have and the strongest one that we have there are London dispersion forces. So this is going to be your water. This is your acetone. This is your benzene. Okay, so now that you have those Lewis structures, please pause the video and rank those. Alright, so let's see how you did. So for the liquids benzene, acetone, and water, rank in increasing surface tension. So the one that's going to have the most surface tension will be the one with the strongest intermolecular forces, which of course here would be water. So the weakest one would be the one with the weakest intermolecular forces, which is benzene, which only has LDFs. Acetone's right in the middle with dipole-dipole. So your benzene is the weakest, followed by acetone, followed by H2O. All right, boiling point temperature. So at boiling point temperature, same thing. Also is following your intermolecular force trend. How much heat are you going to have to put in to break these bonds? Well, the one with the weaker forces isn't going to require as much. So again, benzene is going to be the weakest. And then finally, equilibrium vapor pressure. So equilibrium vapor pressure, remember, this is the tricky one. So if we go back up here, if we have a higher equilibrium vapor pressure, that means that our intermolecular forces are weaker. Because to get all those molecules up there, they had to break through from the liquid phase. You had to have all those intermolecular forces broken. So this trend is actually the opposite. So your H2O is going to have the lowest equilibrium vapor pressure. It's going to be the least volatile. Followed by your acetone, followed by benzene. So benzene is completely nonpolar. So let's go ahead and summarize that down here. Benzene is nonpolar and has only LDFs. Acetone has dipole-dipole attractions. And H2O has H bonding, which is the strongest. So use the Lewis structures to be able to determine that. Alright, so that is the end of the second video on the properties of liquids. The last video that we'll have is gases. That is part 3. So as soon as you're ready, go ahead and start that one.